Okay, we're going to start with our first video for the transformations unit for Math 30-1. Our first topic in transformations we're going to look at today is translations, and we're going to look at both horizontal and vertical translations. So before we get started, a quick review of Math 20. In Math 20 you would have dealt with quadratics, and we would have looked at equations something like this. So if we had something like x minus 4 squared, and let's suppose plus 2. So remember, our regular quadratic of y equals x squared is our quadratic that just goes through the origin. So that's this black graph that I've got on this picture. So that's our regular y equals x squared. So if you remember from Math 20, we would often look at this equation in vertex form, and the reason we called it vertex form is that gave us the coordinate of the vertex. So remember the negative 4, the p-value is 4, or 4 to the right, so our vertex would be 4 over, and then the plus 2 is our q-value, or our vertical amount, which would be 4, 2. So you can see in this picture, we've moved that vertex over to 4, 2. So we're going to be doing similar kinds of things, but we're not just going to focus on quadratics. We're going to be looking at all types of functions. So you can see from the black to this red graph, it is just a translation. We went 4 to the right, and then we went 2 up. But what's interesting or important to note is every coordinate has gone 4 over and 2 up. So if I picked a coordinate like this one right here that's at 2, 4, it's also gone 4 over and 2 up. Like it's made the exact same transformation. Okay, so this blue one that I've got on here, it would have gone to the left. So if we kind of count from the vertex, it looks like we went over 3 to the left. So as an equation, that would be plus 3. And then we went 4 down, so that would be minus 4. So you might remember that from Math 20-1, and that's kind of where we're going to start today. We're going to be doing the same thing, but like I said, not to just quadratics. So where we're going to start with is the definition of a translation, which basically says a vertical translation will move the graph up or down, and a horizontal translation will move that function left or right. Okay, and like I said before, every translation always moves each coordinate on the graph the exact same amount in the exact same directions. Otherwise, the graph would get distorted and kind of weird looking. So it's always going to be the exact same shape, just moved left down or up or right. Okay, so we're going to start with vertical translations because they tend to be a little bit easier. So a little bit new notation. In Math 20, we use sort of a P and Q to indicate the vertex. As a general transformation form, we're now going to switch our letters up a little bit. So if I just give you any function, it doesn't matter if it's a quadratic or absolute value or a linear graph, any kind of function, we can take that function and move it a certain units up or down. So our equation that we're going to use for vertical translation is f of x plus k. So the k value would tell you how many units you're going to move up or down. So for example, I could say f of x plus 2. So that would take whatever our graph is, and I'll just stick with a quadratic again. So if we had some sort of quadratic function, we would take that graph and we'd move it up 2. So it would just be a vertical translation 2 units up. Okay, and we know from other algebra we could actually rewrite this slightly different. I could move the 2 to the other side. So we'd have it as y minus 2 equals f of x. Same thing, that would still be up 2. Because this 2 can be flipped on either side, we're not doing anything different. So you just got to be careful when you see an equation. You sort of want it on the right-hand side of the equation, and it's normal. If it happens to be on the left, you just got to remember to kind of do the opposite side. So, like I said earlier, every coordinate moves the same amount. So in this case, well, let's just stick with this f of x plus 2. So that means every coordinate on that graph, whatever function we're starting with, if we're moving it up 2, that means our x-coordinate doesn't change, only our y-coordinate has been adjusted. And in this case, it'd be adjusted up 2. So it makes no difference what the coordinate is. If I had some sort of coordinate of 3, 7, let's suppose that was on our original function, and we did this f of x plus 2, we'd have 3 would stay the same, and then our 7 coordinate would go up 2, so we'd have 7 plus 2 would give us 9. And we could do that with every coordinate on the graph, and sometimes it works well to help you sketch out the new graph, is just pick a few coordinates to get an idea of what's going on. Okay? And the last note I have on there, just to remember, if it's on the wrong side of the equation, just remember your sign has to get flipped. So be careful of where those numbers are located. So again, we'll kind of go back to quadratics because that's what you're familiar with. So you can see here, our equation if we had y minus 4. The 4 is on the wrong side, so that would be plus 4 if we brought it over. Right, move it to the other side, it'd become plus 4. So you can see that we have 4 units up. And you can kind of see in the bottom picture here, that's exactly what we've got here. The graph, the original red graph, has moved up 4 units. But again, it's not just the vertex, it's every coordinate. So you can see this one here is now also up 4. Or a coordinate up here has also gone up 4. So every coordinate goes up 4. And the blue one that I have, again, the 3's on the wrong side. So if we bring that over, it would be minus 3. So in this case, we moved it 3 down. And then you can see on the blue graph, all of the coordinates are down 3 units. Okay? So pretty simple to deal with vertical translations. You just got to be careful of the plus and minus signs to make sure you're getting the right direction. Okay? And then you can see we have the mapping there. It went to y plus 4 for the green one, y minus 3 for the blue one. And then there's a couple coordinates that were adjusted accordingly. So we'll take a look at horizontal translations now. They're very similar. And again, you've kind of covered this already in Math 20, so shouldn't be too tough to remember. So a horizontal translation, you can see, if you kind of think back to when I originally had that first quadratic equation, we had something like x minus 2 squared plus 3. So we've just sort of dealt with this plus 3 at the end. That was our vertical translation. So the 2 inside the brackets is going to be our horizontal translation. So instead of using P and Q like we had before, we're now using H for the horizontal and K for the vertical. So you can see our equation for horizontal now is f of x minus h. So you might remember from Math 20, again, like we go back to this example, we had a minus 2, but that did move the vertex 2 units to the right. And even though it's minus 2, it went kind of the opposite direction. And that's why we put the negative in the equation, kind of to remind us to do the opposite. So if our h value in this case is 2, we have minus 2, that means we went 2 to the right. Okay, maybe writing it as h equals 2 is kind of confusing, so let me kind of change that quickly. Oops. So our equation, let's kind of just put the equation back in. If we had something like y equals x minus 2 squared. Okay, so that minus 2 would mean 2 right. If we had something like f of x plus 4, now the plus 4 would indicate 4 left. So you just got to remember with horizontal to kind of do the opposite sign. And again, because we're dealing with horizontal translations, it's going to be our x coordinate that's going to change this time. And that's it. So you can see the notation's almost the same. So again, let's just use this 4 to the left one. So let's suppose I had an original coordinate of 3, negative 2. And we're going to move that graph 4 left. So our x coordinate would be, if we're going 4 to the left, we're actually taking away 4. So we'd actually have to have like x minus 4 in our mapping. Let me just kind of write it in here. So our xy would change to x minus 4y because we're going left. So our 3 minus 4 would give us negative 1, and the 2 would stay the same. Negative 2, sorry. Okay, so you just got to be really careful with the signs for horizontal because it is always sort of opposite. A good way to remember is your equation will be opposite, but the words, the mapping, the graph, all of that will match according to logic. And we'll look at a few examples in a minute. Okay, so again, you can kind of see from quadratics, this green graph, we have a minus 3, but again, it's the wrong way, so we'd say 3 to the right. So you can see in the picture here, all of the green from the red is 3 to the right. And then the blue one is plus 2, so that would be 2 to the left, so it's shifted 2 to the left. And again, we can do the coordinate mapping or however we want to describe it. So now that we've done both, let's look at a few questions where we have both horizontal and vertical at the same time. So if we put the two sort of equations together, you can see we get f of x minus h, where h is our horizontal, plus k, where k is the vertical. And again, though the k could be flipped to the other side, or we could always kind of have to rearrange or simplify the equation first. So if we do the mapping, the h will apply to the x coordinate and the k applies to the y coordinate. So let's go through an example. So here's an equation. It says our original graph is absolute value of x, which sometimes they give you the equation, sometimes they don't. It really doesn't matter. And it says we're going to do this translation to that graph. So often they'll ask, what's the description, or describe what's going on. So that's just basically saying what's happening in English and give me a written description. So if you look at this, we have a -4, so that's our horizontal. So we'd say horizontal of 4, and it's minus, that means it's going to go to the right. Okay, I'm writing it all out, but often we just write 4R just to make it a little bit easier. And then the -6 would mean we're doing a vertical translation of 6 down. Okay, so we have our sort of description in words. So now it would be nice if we kind of do a quick little mapping. So our XY coordinates, whatever they happen to be, they're going to change. If we go 4 right, that means we're going to be moving it to the right. We'd be adding 4. So we'll write x plus 4 for the y coordinates. 6 down would be y minus 6. Now that we do that, we can actually apply that to any coordinate we have. So you can see here I give you 3 coordinates. Let's just quickly figure those out. So -5, 5. If we go 4 to the right, that would turn it to, so -5 plus 4 is -1. 5 take away 6 is also -1. So that's where that coordinate's going to go to. Let's keep going. 0, 0. We're going to add 4. That would make it 4. We're going to take away 6. That'll make it -6. Do the same for 5, 5. Add 4 would make it 9. Take away 6 would make it -1. So once we sort of have coordinates, it's often quite easy to sketch the graph. And I don't have quite enough room, but I'll just do a quick sketch here. So our original graph, let's just sort of estimate -5, 5 to be, so there's -5. 5 up would be something like that. Then we'd have 0, 0, and then +5, 5. So our graph would be kind of like that. Okay? So now let's plot our new coordinates. So our -5, 5 turned to -1, -1. So it'd be down here somewhere. The 0, 0 went to 4, 6. So 4 over 6 down. So something like that. And then the last one is 9 over 1 down. So maybe somewhere in there. Okay. Oops, I didn't draw that very good, but you get the idea. Okay. So we'd have sort of our 3 points getting transformed. So again, if we kind of counted spaces, each one should be 4 to the right and 6 down. So 4 over 6 down, 4 over 6 down for all 3 of those coordinates. So working with coordinates definitely helps when it comes to drawing the graph. Sometimes you know, if it's not too tough an equation, you can sort of figure it out without the coordinates, but it's generally a pretty good strategy. Okay, one last thing we're going to look at when we're dealing with graphs and transformations is what happens to our domain and range. So you might remember from earlier math classes, domain stands for all of the possible x values of a function, and the range is for all of the possible y values of a function. So some common examples are, let's just start with an easy graph that was like a linear graph, where the graph just went on and on forever in both directions. We often said the domain was just any real number, and the range was y is any real number. So I just wrote the shorthand version, but remember the way we'd completely write this, we would say for domain we have all x values such that x is any real number, and that's it. So we just kind of use those little squiggly brackets. And the range would be the exact same thing except for y. Okay? But we don't always have graphs like that. So let's, for example, suppose we had a graph that started at 4 and went down to -3. So let's suppose we have a point, you know, something like this. So let's suppose we have a graph that does, I'll just draw this as an open dot, and let's suppose it goes down to about -3. I'll just kind of do it as a quadratic or something like that, and then carries on forever. Okay, so a couple things to remember from earlier math classes. When it's less than, that means that point wasn't included, so that's why I kind of drew it as an open dot. And if it's greater than -3, that means the coordinates touched -3, it actually included -3, and then it did everything above it. Okay, and again, we would probably write these in better notation, so we would say x such that x is less than 4, where x is any real number. Okay, and then the last example I have here is where it's between two numbers. So, for example, I'll just do this -2 to 5, so our graph would start at -2, but you can see it's less than, so there's not including 2, -2, and it would go up to 5, where 5 is included. And our graph could do anything in between those two. Let's just suppose it does something weird like that. So that would be our domain for that graph. And the range, again, the way I've sketched it here, this would be at 0, and I've got a maximum of 12. So this peak up here would go way up to 12 or whatever. Okay, so you should remember doing domain and ranges. They're all kind of the same sort of thing once you get the hang of it, but remember it's just listing all of the possible x and all of the possible y values. What we're going to look at this year, we're still going to be dealing with domain and range, but we're going to introduce a new notation. So interval notation, it does the same thing, it's just a different way of writing it. And a lot of people like it better because it's a little bit simpler to write and kind of often makes more sense. So the only thing that we got to be careful of is if we have, let me just kind of go back to that one I just sketched. So if we went from -2 up to 5, and let's suppose we had an open dot at -2, closed at 5, and our graph did something in between there, we just said that we would write it as from -2 to 5, less than, and then less than or equal to. So that was the way we wrote it in the old notation. The new notation, interval notation, we basically just write our first number, the smallest number first, the largest number second. So you can see we just use the -2, 5. You almost write it like a coordinate, but it's not telling us a coordinate. It's saying the domain starts at -2, ends at 5. And then we use the round bracket at the -2 side to show you that it's open circle. And then we use the square bracket on the 5 side to show that it's equal to 5. Okay? And that's it. So a lot of people like it better just because it's a little bit quicker to write. And when we get something like x is less than 4, let me just kind of put that on a number line. So that means we'd have open circle at 4, and we have our graph that goes everywhere below that. So then again, 4 would be our maximum. Our minimum is everything below it, so the best way to write that is just -infinity. Anything below 4 would go all the way down to -infinity. You'll never equal -infinity, that's why we have a round bracket, and in this case we don't equal 4, so it's a round bracket as well. Okay, and if we had a graph where we had XER, any real number, that means it can go from positive infinity to negative infinity, so we often just write that, negative infinity to positive infinity. And the notation works exactly the same for the range, it's just where you're talking about the y coordinates. So let's do an example or two just kind of dealing with this from start to finish. So this picture, I've got a graph drawn, and you can see it's just some sort of random collection of dots. It's not really any function, but it is a function. So we don't know what the equation is, but we don't really need to know. We just perform whatever transformations we want. So we have that graph. It's asking us to do this transformation. So let's figure it out first in words. So the +2 would mean we're going to go 2 to the left because it's opposite direction. The -5 would be 5 down. So what that means is we're going to take every coordinate and go 2 left and 5 down. So again, if we wanted to write the mapping out, that means our xy coordinates are going to change to x -2 for the left, 5 down would be y -5. Okay, so we're going to do that to every coordinate. So this first coordinate on the graph that's at -3, 0, it would go 2 left and 5 down, so it would move it down to about there. And we can do that with all of them, move it 2 over, 5 down would be to about there. The peak there is 2 over, 5 down would be to there, and keep on going. 1, 2, 1, 2, 3, 4, 5. So it should be right there. Okay, so if I connect those dots, that should give me the new function that's been transformed 2 left and 5 down. And that's it. So let's do the domain and range because there is some neat things that happen here. So if we look at the domain on the original graph, let me just kind of write them up here. So in that original black graph, our domain started at -3, and you can see it ended over at 6. So our domain is from -3 to 6. Our range, we're starting at 0, and we're going up to 5. Okay, so it's pretty easy to write that. So now let's do our domain and range of the new one. So the new graph that I drew, the domain, you can kind of see I went over here, so that's at about -5. And you can see it's ending at +4 now. And our range, I think I went down 3 spaces. Let's just double check again. So we went 2 over and then 5 down, so 1, 2, 3, 4, 5. Yeah, so we're at -5. And you can see the top of it now is at 0. And that's it. So pretty easy to do the domain and range. You can do it from the graph, but we can also do it from the transformations. So if we kind of go back to what we have here in words, we went 2 left and 5 down. So if you actually compare the domains, if we look at this domain to here, you can see each coordinate of the domain has moved over 2 left. We basically just subtracted 2 from each of those. -3 minus 2 gave us -5. 6 minus 2 gave us 4. And the same thing happens for the range. Our range was 5 down. So if you compare the two range values, we basically just subtracted 5 from both of those. 0 take away 5 and 5 take away 5. Okay? So if you know the starting domain and range, you can actually figure out what the new domain range is without ever seeing the graph, and it works quite well. So let's do one more. Here's where we got two graphs, and we're just asking what's the new equation and what's the new domain and range. Okay? So it looks like you got to be a little bit careful here. Our original graph is y equals fx. So the dotted line graph is the original, and we're moving it up to this block graph. So again, you can kind of work coordinate by coordinate, but usually you can kind of figure out the transformation pretty quickly. So if we look here, it looks like we went 2 left and 4 up. And we can just double check that with a different coordinate. Let's go here, 2 left, 4 up. They all look like 2 left, 4 up. So we're good. So if we have 2 left and 4 up, we should be able to figure out what that equation would be. So in terms of the equation, the left being 2 to the left, that means we'd have plus 2. Let me just erase that here so I got room to write it underneath. Okay, so we had 2 left, 4 up. So the 2 left would be x plus 2 going to the left. The 4 up, we'd have a plus 4 on this side, but you can see I want it written the other way around. So if we move that 4 over, it would be y minus 4. So that should be our equation for this transformation. Y minus 4 equals f of x plus 2. And again, we could do the domain and range. So let's just write that out quick. So our original domain went from, looks like -3 to +4. And our original range went from -5 up to +3. So if we do that transformation, 2 left, that means we're going to move everything over to the 2 in the domain. So that means we're going from -5 to over to +2, which looks right. You can see here this graph starting at 5 and it's ending at 2. And then our range, we went 4 up, so we should add 4 to each of them. So that means we're going -1 to 7. And again, we can kind of see that's at -1 and it ends at 7. So it does work pretty good. Okay, let's do one more. So the dotted line again, this quadratic is our original graph. We've moved it over. Looks like we went to the right 6 units and looks like we went down 7. So again, as an equation, let's do the right first. Right will be negative in the equation, so x minus 6. Down 7 would be -7, but again, let's move that to the other side, so that should be +7. So y plus 7 equals f of x minus 6. And our domain and range would work pretty much the same. We won't bother wasting time going through that. So that's it for our first topic. We've got left-right translations, up-down translations. Just be really careful whether they're positive or negative so you get your direction right. You can draw the graphs, you can write the equations, you can figure out coordinates. It's all interchangeable. So that's it for today. We'll look at stretches, vertical and horizontal stretches, in the next topic.